Our next talk this morning is from Andy Wilson. He'll be talking about an extension of MacMahon's Equidistribution theorem to ordered multiset partitions.
Yeah, I know, it's a long time. Thank you, and thank you guys for listening today. Alright, so by MacMahon's Equidistribution theorem, I really mean the fact, the maybe sort of elementary fact, that the inversion number and major index have the same distribution over permutations. I'll talk about this a little more. And in particular, I'll talk about it sort of via the lens of Karlitz's insertion method proof, which is, I think, well, less well known than Kawada's bijective proof because it came later, fair enough. But it tends to be the one that actually works best in this setting. So I'll talk a little bit about that. And in particular, our sort of main result is an extension of this equidistribution to a new set of objects, the set of ordered multi-set partitions. Or really, I'll talk probably more about ordered set partitions today, just for time reasons. And that means we have sort of a new inv and a new maj on these objects, and we can show they have the same distribution. And there are some sort of nice consequences of this fact. Some applications of Q-Eulerian numbers to answer a problem posed by Stein-Grimson. A recent conjecture of Hagelin about diagonal harmonics, which is somewhat related to what Emily just spoke about. And some sort of more experimental work on adding some new parameters to McDonald polynomials. We've only been able to do this for hook shapes so far, but maybe we can do more. Alright, so just to set some vocabulary, statistic, I mean a map from any set to non-negative integers, and some sort of classical statistics include descents, inversion number, and major index. So inversion is sort of the number of pairs that are out of order. Major index is the sum of the positions of the descents in a permutation. And just to make sure we're all on the same page, here's an example. This permutation has 3 descents, 6 inversions, which I won't count in front of all of you, but I'm pretty sure that's right. And major index equal to 7. Right? So distribution is just the sum of Q to sort of the value of the statistic over all elements of the set. So it's a polynomial. And we can sort of compute the distributions of inv and maj over S3. If we really feel like it, here's inv, here's maj. And you see that they have the same distribution. Of course, this is no coincidence. So if you first notice this, I mean, you would have had to first notice it about 100 years ago or so, probably further away. You might think, well, is this always true? Well, yes. And is there sort of a map from S3 to itself such that this map sends things with inversion number k to major index k? And the answer to that is also yes. So even better, we can give a nice sort of description of what this polynomial looks like. It's the Q analog of n factorial, so the product of all the Q integers from 1 up to n. So this is what I mean by MacMahon's equidistribution theorem from around 1915, that the inversion number and major index are both Mahonian statistics on Sn. By Mahonian, I mean they have this distribution. All right. And in fact, his original proof was sort of more analytic, so it took a relatively long time until there were bijective proofs. The first one due to Kawada, and this one I'll talk about today is attributed to Karlitz. The idea is to prove these two recursions combinatorially. That when I go from Sn minus 1 to Sn, I just pick up a Q integer of n, and this is, I think, pretty clearly equivalent to showing that we have the right distribution. And the idea is to just build up permutations by inserting a new largest element. So I'm going to pick a spot to insert. In this case, it would be an 8. I'm going to put it between the 2 and the 1. And I'm going to count how many new inversions I've created. I haven't created any inversions, but I've added, in this case, it will be 5 more. And in fact, I can use these little labels here to sort of record how many inversions I would add if I put an 8 there. So if I put an 8 here between 2 and 1, I get 5 new inversions. And this, yeah, this is red, but you can take my word for it. This should be, this is the Q integer of 8, which sort of shows up here. So you have these 8 choices, and they give you these 8 possible increases in inversion number. Okay. And even better, this labeling here is independent of the permutation. It just matters how many things are to your right. All right, so this will be sort of a running theme, but the major index side is a little bit harder. In particular, we have the same recursion, but now the labeling will depend on the permutation. The labeling goes like this. You start with a 0 on the far right, and you label from right to left the descents. And then you label everything else from left to right. And what I mean by that is if I put a new 8, say, here, between the 1 and the 5, I would increase the major index by 6. It's not quite as obvious, but take some cases, but it's something that can be looked at. And again, we have this Q integer of 8 sort of showing up here. And these maps give a bijective proof of equidistribution. But what I mean by that is you can sort of start with the permutation, sort of break it down by repeatedly taking out largest elements and counting how many inversions you lose. And then use that to sort of choose what label you're going to insert a new number in using the major index labeling. So we go from 52143 to 24153. And indeed, you can check these have both 6 inversions and the major index equals 6. And more than this is known, if you deal with permutations of some multiset, so you might have more than one copy of some number, these still have the same distribution. We still have a nice formula for this distribution. And in fact, even this insertion method can be modified to work. So this is pretty recent, actually, due to Radhan, and this paper is on polyominoes, I believe. Moon polyominoes. And the idea is, so what happens if I want to insert, 5 new 8s? I have to sort of label this in some way and do things in some specified order so that I add the right number of inversions or major index. So unfortunately, I don't have time to go into this, but so this is pretty useful. And sort of the main idea of this talk is if we can extend these ideas to ordered partitions. All right, so this sort of insertion method process. So I'll set OP sub nk to be the ordered partitions of the numbers 1 through n into k blocks. So here's some examples, and there are many different ways of sort of writing these things down, and that turns out to be actually surprisingly important. So this is one sort of semi-classical way to do it, is that I'm using bars to sort of split up the blocks. And I break each block in descending order, just because these are sets, so I just have to pick some way to do it. Or I can write this, and I can use stars to sort of connect things that are in the same block. So stars are sort of the connective identifiers. And here I haven't put in any bars, but I guess I could if I wanted to. And here's another way. We're just writing each block sort of vertically down. So there's no necessary relationship between the rows here, but the columns would have to be strictly increasing as you go up. So these are all the same ordered separation. And each of these will sort of play a role. So let's start with defining inversion statistics. So this is previously known also, and there are many different ways you could start here. This just turns out to be maybe one of the easiest. So let's say that the inversion number of an ordered set partition counts the number of inversions ending in the bottom row. So that's vague. I'll try to show what I mean by this example. So if I sort of go along the bottom row and I count the number of things strictly to the left of it that are greater than it. So here I have just one inversion between the 6 and the 5. I have one inversion ending at the 8 between the 9 and the 8. At the 1, there are lots of inversions. These, 6 things all end at the 1. At the 3, we have these, 6 things. So I have the sum of what the numbers I just said, that many inversions. And please let me know if there are any questions. So in this paper of Steingrimson, he showed that this inversion statistic has a nice distribution in terms of these Q Stirling numbers. It's awfully low, sorry about that. And there are multiple sort of Q Stirling numbers of the second kind floating around. This is the one without a Q to the K here. And in fact, this recursion can be sort of defined, this distribution can be defined by this recursion here, where if I pick an element of OPn minus 1k or OPn minus 1k minus 1, I get a Q integer to produce an element in OPn k. And we'll call this Mahonian distribution on OPn k. So I'll be egregiously reusing terms from the symmetric group case. So this is a nice distribution, and you might wonder, is there sort of a MAS statistic that has the same distribution? But before we do that, let's give an idea as to why this is Mahonian. So we'll go back, we'll use essentially this recursion, sort of give a sketch as to why this recursion is true. I wanted to say one more thing here, which is if you're familiar with rook theory, this probably rings some bells, and I'll say a little bit more at that at the very end, but I won't talk about it very much. All right, so the idea is to consider inserting a largest element, a new largest element, like last time. But now there are two ways to do this. We can do it in an existing block, or we can create a new block. So let's start with this ordered set partition. I've drawn it like this. And I want to put a 10 somewhere. And the idea is I could put it in an existing block, and that'll give me, if I put it, say, here, I would get 4 new inversions. Here would be 3, 2, 1, 0. In particular, if I choose this 2, I put the 10 here, and I get 2 new inversions between the 1 and the 10 and the 1. And if I form new blocks, I would get this set of increases in inversion count. So for example, if I chose a 0, I put the 10 at the end, and I get no new inversions. And the idea is that these sort of represent Q integers, which go back to that recursion on the previous slide. So this is not a proof exactly, but this is sort of the thing that we look for when we're proving such a thing. And these labels should probably be shifted over slightly, but my Beamer skills aren't that sophisticated. All right, so this is an argument that inv has this nice distribution, or at least this nice recursion. And well, before moving on to MAJ, we actually can produce another inv type statistic, and this one I believe has not been studied before. And I'll call this one the diagonal inversion number, or DINV. So this should somewhat remind you of parking functions, except it'll be reflected. It counts the number of inversions between an element and the elements in the next row in reading order. So the idea is say this 7 only sees elements to its right or below it to its left, and it stops seeing elements at 5. So for example, there are lots of slides here with different colors, but anyway. So I'll just keep clicking here. So if I start at the 6 sees the 7, but there's no inversion. It sees the 4, which is an inversion, and it stops seeing things at the 2. It doesn't see the 2 because it's below it. So you sort of just go until you reach below where you started. And you do that for each element. So from the 7, it sees the 4 to the 5. And you count inversions that way. And the idea is, well, I can do some labeling again. If I put, say, a 10 up here, I get no new diagonal inversions. I get 1 here. I'm sort of labeling these in sort of top-down order. So top-down, left to right. So 0, 1. And this might be, no, 2, 3, 4. You can maybe check that putting a 10, say, here is going to give you 4 new diagonal inversions. And if I'm starting a new part, it's easier. It's the same thing that happens before. You just get inversions in the bottom row. Okay. So again, we have the same distribution as before. So DINV is Mahonian on OP. Okay. So finally, a major index here. The idea is I'm going to start with this sort of barred representation. And I'm going to come up with a weakly increasing sequence by increasing my current number by 1 each time I hit a number that's followed by a bar. So that was kind of a mouthful, but the idea is each time, since I get to 2 and it's followed by a bar, I go from 0 to 1. I don't increase here, but 5 is followed by a bar, so I go from 1 to 2, then 2 to 3, 3 to 4 here because 1 is followed by a bar, and so on. And these will be sort of the numbers I add up that correspond to the sense.
Why is the last one at 5?
That's a good question, I guess. Is 3 followed by a bar or not? I guess not.
It's a bar there, it's just colored.
Yeah, right. It's colored white or something. Yeah. It turns out not to matter because there's no descent at the last element, so you'll never pick that one. But it's a fair question. It probably should be. So what I'll do is sum up the elements in this weakly increasing sequence that correspond to descents. So again, some things have turned red here. This 6, this 0 here, this 1, 1, 3, 3, because these all correspond to descents in the ordered set partition. And I sum those up, and that's going to be my major index. And again, the result here is that this statistic has the same distribution. It's Mahonian on ordered set partition. All right. So this is a bit more technical. I'll be very vague about this. The idea is that we need to construct ordered set partitions differently. Rather than just plopping a 10 in a new block or as its own block, we do something more complicated. We sort of pick a position. So now I'm using this starred idea. I'm going to pick a position where there's no star, and I'm going to say put a new 10. I'm going to put a 10 there. Okay. But then I'm going to move every star to the right of this 10, 1 descent to its left. Okay, so you'll see that I put a 10 in here, and I move this star that was on a 4 to the 8, because that's the descent to the left of the 4. I move this star from the 7 to the 9, because that's the descent to the left of the 7. Okay. And And finally, this represents the sort of two different types of insertions. I decide whether or not to star this rightmost descent. So after step 2, the rightmost descent will be sort of blank, and I can decide if I can star it or not. And remember, these stars represent things that are in the same part of the ordered set partition, the same block. So why would you want to create ordered set partitions this way? It seems much more convoluted. And the idea is that we can label these positions and sort of keep track of this major index statistic. So if let's see, here I decided to put a 10 between the 2 and the 9. If I don't decide to star the last thing, I would get 3. My increase in major index would be 3. If I do, my increase would be 2. So I can sort of track through this process what happens to this major index statistic. And it's, there are a number of cases, but it can be done. So these labels, again, are sort of representing the Q integer, that Q int of k that shows up in the recursion. All right, so this is sort of all of our results in one spot here, that all these statistics have this distribution over ordered set partitions. And in fact, like in the permutation case, they have the same distribution over ordered multiset partitions, where ordered multiset partition, if I take a multiset and I split it into some blocks which are sets, I'm assuming the blocks are not multisets, tends to work better for the major index side. So these have the same distribution. We don't really have a nice expression of this form. If you have the same number of copies of each element in your multiset, so you have, say, 3 copies of every number, then you can write this, you get a R analog of Q Stirling numbers. So you can write it in some sort of Stirling type thing in this form. But in general, there's not a nice way to write the polynomial. And there's an alternate way to formulate at least the inv and maj part of this, which is so this was all originally conjectured by Jim Hagelin, and this is the form he wrote it in. The idea is I can write it as a sum over permutations, and at each descent in the permutation, I can either decide to star it, in which case I have to do something to the inversion number, or not star it, which means that I have a new block, which means I pick up a sort of z here. So we get this sort of distribution where z counts the number of blocks. So this is just a sum over permutations, and I can do I can also sum over ascents if I write my ordered set partitions and my blocks in increasing order. And you can also do something similar for the major index. The idea is, if you look at the descents from right to left, if you choose to star a descent, you actually take, if you star the jth descent, you take j away from this maj statistic, this maj over ordered set partitions. So we have that this thing equals this thing equals this thing. Here I'm using in box p to be number of conversions that end at some position. So this is just another way to write down the, if you don't like ordered set partitions, this is only about permutations. And in fact, permutations of some multiset. All right, so getting to the applications. So our first one is to these Q-Eulerian numbers. The idea is sort of based on the same idea I talked about in the last slide, that if I start with the distribution of maj over permutations that have a certain number of descents, say b descents. This is the Q-Eulerian number, or one Q-Eulerian number. I can pick some of these descents to sort of star or not, and keep track of maj as I do this, and I get this equality here. And why do we care about this? Well, this satisfies something which was asked for in 2007 by Steingrimson. There's this Q identity here, which was proven using analytic methods, and this is the first combinatorial proof of this identity that I'm aware of. So this sort of maj statistic is the key here, that we can show that maj satisfies its right-hand side, and it has this distribution. We also have this new conjecture of Haglin's. So a lot of this is sort of parking function notation, which fortunately Emily mostly talked about. I didn't write almost any definitions on the slide. So this is din from parking function, area from parking functions. This means that I have 2 consecutive north steps. If I have 2 consecutive north steps, I can sort of throw away the area from the second of those north steps in this polynomial. Or I can choose not to throw it away and I get a w. And x count how many ones are in my word parking function. You can write this in terms of quasi-symmetric functions. So the conjecture is that this is equal to this left-hand side, where this is the delta operator from diagonal harmonics. Maybe it's best just to say that if k equals n, this is the nabla operator, so you get the actual diagonal harmonics module, otherwise you get some other modules. So the conjecture is that this sort of combinatorially captures the behavior of this delta operator, where it depends on some symmetric function, in this case e sub k. And how does that relate to this? Well, we can use these results to prove a sort of very weak form of the QT symmetry here. If I set t equals 0 in this polynomial, you can see that I'll get some sort of distribution of in over ordered multiset partitions. If I set q equals 0, I get maj over some ordered multiset partitions. And the fact that these are equal means that I can sort of put q from here to here and switch 0 from here to here. And again, this is weak form of symmetry of q and t. So we know that this thing should have QT symmetry. In fact, it should have lots more properties, but I don't believe any of those are known. I mean, even just switching q and t here without the 0 is several levels stronger than QT Catalan symmetry, which is a notoriously hard problem. That's why we need to bite off such a small piece. And finally, we've been looking at sort of how to work this into the McDonald polynomial framework. The idea is you can write modified McDonald polynomials over sums of fillings of Young diagrams, such as this. For hook shapes, all I have to do is calculate inv across rows and maj down columns, hit q to that, and t to the maj, and sort of sum over all these fillings. But you can sort of imagine, instead of putting a permutation here, I could put a, say, ordered multiset partition, so I could sort of maybe remove some of these bars or something. And then I can also count the number of blocks in each row, and each blocks in the row and blocks in the column. So we get some sort of extra auxiliary variables here. And for hook cases, we know how to decompose this in terms of Schurs, and we can prove that it's symmetric and things like that. But for general shapes, it's really completely wide open, even like the 2x2 square, because you need to modify these statistics somehow, and it's not clear how to do that yet. But maybe this could lead to some sort of extra parameters in McDonald polynomial. So it would be like QT UV McDonald or something like that. This is still very much in the early stages. And just a couple of other extensions. So you can do this sort of thing with other co-in, co-maj. In fact, you can also do it with this major index of Rawlings, which interpolates between inv and maj. It gets quite nasty, but it works. Because Rawlings define this sort of using insertion method as well. And some things we've been looking at are doing these with sign permutations and color permutations. In this setting, there's sort of a couple different ways to go. They all have their sort of strengths and weaknesses. It's not clear if there's sort of a one master statistic, or if that's just what you have to live with when you move beyond type A. And finally, there's a way to give this entire presentation in terms of rook placements, in particular mixed rook placements, where you have some sort of canceling rooks and some file rooks. If you were at Bruce Sagan's conference in March, my advisor Jeff Remmel gave sort of that version of this talk. Unfortunately, I didn't put almost any of it in the talk today, but if you like rook theory, I'm sure he's not pleased about that. But if you like rook theory, please come talk to me or him, and we'd be glad to tell you sort of the connections to rook theory here. So you can view all this from sort of maps from rook placements to ordered partitions. And I believe that's all I have today. So some citations, and thank you very much.
Questions for Andy? Yes.
Okay, so you've got these basically building rules. It shows you how to make a bigger ordered set for another one. And you got two of them, and and they preserve sort of the statistics in an equidistributed way. So you could look at this as sort of generating some kind of rank closed set of these objects. And what you're describing is a local isomorphism between two spots in the rank closed set. The statistics preserved. Have you ever thought about the whole closed set? What can you say about the structure of the process made by these building rules?
I guess the answer is I haven't really thought about it. It seems I've had a lot of difficulty if I try to do anything but work locally. Maybe, I mean, I guess I'm not sure, so it's a good question. I've only been able to sort of get anything locally. I mean, for example, for a while we tried to do this with like a more full-out type bijection, and just really failed utterly. So maybe there's something about this method that just works, or maybe you can say something more general. I'm not sure.
So when you were doing ordered partitions, you defined in, but you had all the sense, but then you didn't take into account the arms of those sense, which is usually.
Right, yeah.
So that sort of flips it somehow, but then at the end you were trying to generalize McDonald, and I was wondering like,
Right,
where
yeah.
you switched.
So that's really the question is, to actually get to McDonald polynomials, you don't just count in across rows, you correct it, right? Or you take your ordering in some different way. That's the reason why I can't even do a 2x2 box. I'm not sure what this correction is. So this is why rows work and everything else doesn't. Yeah, exactly.
So the equidistribution of match and unique can be applied to some classes. You have something.
Doing it for order multi-set partitions is equivalent to doing for, so you standardize and then you get the distribution over inverse descents. So standardization does do that for you. So we need that actually for some of these applications I said at the end.
You seem to focus on ordered
Yeah.
set partitions. Is there any reason why you can't do unordered? Or if the unordered would be restricting to the first row being inclusive?
I guess I thought about this briefly and I didn't see an easy way into doing just set partitions. There is a fair amount of work on statistics on set partitions. This probably relates to those somehow, but that's about as much as I can say. I didn't see an easy way into